Well, hello everyone and welcome. Happy World Quantum Day. I'm Dr. Svetlana Barkanova, NSERC Chair for Inclusion and Science and Engineering, and it is my greatest pleasure to introduce Dr. Chitra Rangan, who is going to give a talk about adventures in Quantumland. Dr. Chitra Rangan is a professor of Department of Physics and an associate dean of the Faculty of Graduate Studies at the University of Windsor. Her research is in the fields of quantum information and quantum control. She has won multiple recognitions for evidence-based teaching, as well as educational leadership. She is a member of the board of the Canadian Association of Physicists and has served as the chair of a division for gender equity in physics. She is passionate about quantum science, scientific teaching, gender equity in physics, science outreach, and the Indian dance form of Bharathanatyam. Welcome, Chitra. Thank you so much. Take it away.
Hello, everybody. Let me make sure that everybody can see me. Okay. So I'm really happy to talk to you today because it is the International Year of Quantum Science and Technology. This is a UNESCO-sponsored year that recognizes 100 years since the initial development of quantum mechanics. And you can go to this international website that I have here and learn about all the worldwide celebration. In Canada, we also are celebrating the International Year of Quantum Science and Technology by hosting nationwide events all around you. So if you go to quantumcanada2025.ca, you can check out a lot of the local events there. And this lecture series is also part of one of this Canadian celebration. I just want to highlight that this logo made for the International Year of Quantum Science and Technology Canada was designed by Jasmine Zhang, who is a first-year PhD student at the University of British Columbia. And you can contact this website if you would like to access this logo and use it in your own events that you might hold in your school. So the quantum science and for grades 10 to 12 students is a joint initiative of the NSERC Chair for Inclusion in Science and Engineering Atlantic and the Canadian Association of Physicists team Quantum Canada. So along with today's kickoff meeting, we will have talks by a variety of speakers who are both scientists and engineers and people who work in the academic sector as well as the industrial sector. And our goal is to tell you a little bit about quantum science and how you might develop a career in that field. We will also give you some examples of our own participation. So, happy World Quantum Day. This Quantum Day is celebrated since 2021 on April 14th every year. But this year, because it's the International Year of Science and Technology, of Quantum Science and Technology, every day is celebrated as World Quantum Day. So before I begin to tell you about the science, let me tell you a little bit about myself. As Dr. Barkanova already introduced me, I work at the University of Windsor, which is in Ontario, Canada. I was born in India. I grew up with three siblings in big cities. And after high school, I went to the University of Madras for a bachelor's degree, for an undergraduate degree. And this I did in physics with allied subjects, chemistry and math. And then I got exposed to research in my master's degree at the Indian Institute of Technology in Madras when I really got excited about doing research. And then I came to the US for a PhD at a fairly small town called Baton Rouge. And the university was the Louisiana State University. And then After I got my PhD, I worked as a researcher at the University of Michigan for 4 years, and then I became a professor at the University of Windsor. Apart from my academic history, I want to tell you a little bit about some interesting jobs that I've had. I had a job as an assistant radio producer at All India Radio, and this allowed me to use my knowledge of quantum mechanics and quantum electronics to get twice the number of hours that any other producer would get. I also worked as a scientific editor for the company ProQuest, and that allowed me to use my knowledge of science and physics to edit journals and introduce people to what was the most important things in this area. So apart from this, I'm really interested in talking about quantum science, teaching and how to teach well, about in making sure that physics is equitable for people of all genders. I love science outreach, so I participate both International Day of Light as well as Science Rendezvous. And here's me doing the Indian dance form of Bharathanatyam. Okay, so let's get to quantum science. So in today's talk, what I'm going to do is to try to introduce you to some key features of quantum science and technology. And so for each facet of science, I would like to present a technology that we can see has changed our world. First, let's talk about quantization. Let me start with a question. Some of you may know this answer already. What is the formula for the energy of a particle moving with the speed v? It's going to give you a few seconds to write the answer down. If you wrote down E equals 1/2 mv squared, that's correct. This is the famous formula by Émile de Châtelet, and it was known even before Newton. What this formula says is that as the speed increases, the kinetic energy of the particle increases. And it means that a particle can have a speed from 0 all the way to very, very large numbers, and the kinetic energy will also increase in the same way. So this idea has been known for a very long time. It was slightly modified by Einstein when he said a particle cannot have a speed greater than the speed of light, c, but otherwise, as the speed increases, the kinetic energy increases. In 1885 or so, there were experiments that were done by Balmer that showed that if you measure the energy of an electron inside an atom, it's not continuous. It's not as if it can take any value, but it's actually quantized. What that means is that you can actually get only certain values of this energy. And so this was a revolutionary idea, that you could have the energy of something not be a continuous value, but actually a quantized value. So this, even though it was not realized at this time why this was the case, this was sort of the precursor to what we now know as quantum mechanics. Max Planck in 1900 added to this idea and said, well, a body can change its energy only by fixed amounts, and this energy must be emitted as quanta. So this is the famous formula of E equals h times f. So if the energy is only a few things, so if you can go from this energy to this energy, you give off energy in a certain quantum. Einstein added to this by coming up with the concept of photons. And he said that when an electron in an atom, goes from a higher energy level to a lower energy level, then electromagnetic radiation is given off, which we also call light. But the electromagnetic radiation comes out only in certain bundles of energy. And so he says radiation is also quantized. And so this is what we call photons. So you have light photons, gamma ray photons, infrared photons, etc., depending on the frequency or color. So Einstein's hypothesis was that the frequency of light it determines the energy of the light, photon. So these three together were the foundation of quantization. Now, where can we find an application of this? An application of this is in nuclear magnetism. So sometimes you may have heard of the word MRI. And is because the energy of protons and neutrons and electrons are quantized. They can go into one of two energy states in a magnetic field. And when you put an external RF field to switch the state from an upper level to a lower level, then it gives off radiation, and that's what we measure. So these are examples of um MRI images that are um that you can see in showing us this very high contrast. And this contrast is possible because of quantization. Now let's talk about another quantum science idea, which is wave particle duality. In the classical world, before quantum mechanics existed, people thought that the whole world was made up of behaviors that are particle like, which Newton liked very much, and wave like, which many people, including Christian Huygens, liked very much. So, particle like behaviors meant that you could point to something and say, the particle is here. You could say, the particle moves from here to here. The wave like nature, it talks is like it's very spread out. So think of a wave of water. You can't say where it is. It's everywhere here. And you can't say where it's moving exactly. You can only talk about an evolution. So let me show you a picture to make this idea. So here you see a surfer who's on a wave. For the surfer, I can say the surfer is here. I can point to it with my mouse. I can draw a line and say the surfer goes from here to here, right? So I can draw a trajectory, very clear. Now, on the other hand, if I looked at this wave, excuse me, the wave, I cannot tell you where the wave is. This whole thing is a wave. It's very spread out. And the whole thing evolves. So if I tell you where is this wave going, I have to tell you this part goes here, this part goes here, this part goes here, this part goes here. Right? So waves and particles behave very differently. Now, how do we know how waves behave? One of the signature of waves is that they undergo interference and diffraction. So, for example, you have two waves that are coming here and meeting up, and you see how this pattern is that at some places they are very bright and some places they're very dull. So, this is called interference. And this interference is a signature of wave behavior. Now, we see this all the time. If you look at sound waves, so supposing you go to a concert and there are two big microphones in the two big speakers out in the front, and you can walk on the back of the room, and there are some places which the sound is very clear, and in some places you don't hear it at all. So that's an example of wave interference. Okay, so you have a wave, here's one speaker, here's another speaker, and when you have both speakers, the two waves interfere, and you get places where you hear very well and places where you do not hear very well. So just excuse me while I take a sip of water. Now, this interference is seen in light waves also. So this interference is seen in light waves also. As you see here, this is a red light that is going through these two slits, and you see these patterns of bright and dark spots, which we call fringes. So we know that light is a wave. Now, in 1924, there was a prince called Louis de Broglie, and he made a hypothesis. A hypothesis is an educated guess. And he said electrons and other particles of matter can also behave like waves. And they have a wavelength. And the wavelength is going to be equal to the Planck's constant h, which we already saw before, divided by the particle's momentum. So the momentum of a particle, if it's very large, the wavelength is very small. If the momentum is very small, the wavelength is large. Now let me ask you, have you learned about momentum in school? What is the formula for momentum? You can put it in the chat if you like. The formula for momentum is mass times velocity. So if the mass of an object is very large, that means the momentum is large, and therefore the wavelength is going to be very small. And if the mass is very small, then the wavelength will be large. So this is why if you have an object like a baseball, its wavelength is going to be extremely small because its mass is huge. So you cannot see these wave aspects of macroscopic objects easily. So Louis Broglie suggested, supposing you look at a very small object like an electron, then you might be able to see its wave behavior. So there were a lot of people who thought that let's do this experiment. Let's do this two slit experiment that we just saw with sound and light. Let's do it with electrons and let's see what happens. So this was what was done. And the result was very interesting. So when they did the experiment, you saw these electrons coming and hitting the screen. Okay, no big surprise. And then, but just wait long enough and see what happens. More electrons hitting the screen. Each dot is an electron. It hits the screen. It hits the screen. Still going on. And when you get to about 200,000 electrons, then you begin to see stripes. And these stripes are the same interference fringes that we saw before. Let me just stop this so you can see this clearly. So see that? So you can see these fringes. So what does this mean? Let's think about this. So suppose I'm just going to try to move this down to the bottom of the screen. So if electrons were particles, then what you should see is with this two slit experiment, you should see just two clumps. That's it. You shouldn't see anything else. But what you're actually seeing is that in the two slit experiment, you're seeing an interference pattern. So this is a signature that electron is a wave. Okay. So what this tells us is that this electron diffraction image confirms to us that matter can behave both like a particle. So when it hits the screen, it makes a dot. So that's a particle-like behavior. And it exhibits wave-like behaviors. So this is called wave-particle duality. Now, you can use this wave-particle duality to do something called electron microscopy. So what you can do is to decrease the wavelength to very small amounts, and by increasing the momentum, and therefore you can actually see a microscope of this is an electron microscope image of viruses on top of a bacteria. So this is extremely a small thing. So you can see here at the bottom of the scale, this is about 1 micrometer. And so you're actually seeing things that are less than about, this is zero point 0.1 micrometer, which is 100 nanometers. And so this means this is an extremely small, about 10 nanometer size that you're able to see with an electron microscope. Now, next idea I want to introduce you is the idea of uncertainty. Uncertainty is, let's think about this for 1 minute. So there is a probability wave attached to an electron. This says that an electron is a wave. It has a certain, if you want to say, where is the electron? You say, okay, the electron is here. And if you want to say, well, how sure am I of where the electron is? That's determined by the width of this wave. So if I have um, this wave, it tells me what if I say every material particle like an electron has a wave nature associated with it, then that means it also has a certain uncertainty. So let's say I have a wave packet. Different parts of the wave packet can move with different speeds. So this means that the position of the speed of an electron are measured, there is a spread. And this is called uncertainty or indeterminacy. And that's associated with both quantities. So Heisenberg he came up with this uncertainty principle and said that the position and speed of every material particle cannot be measured exactly. You cannot know exactly the position or the speed of any small particle. It's always uncertain to a very, very small amount. But if the mass is greater, then you can be more precise. The more greater the mass, then the more precisely you can measure the uncertainty. So this principle basically means that supposing you have, if you draw the position on one side, how well you can measure the position and how well you can measure the momentum. For a small particle like a very light particle like a proton, it's somewhere here. You can measure the particle, you can measure the position very well, but not its momentum. Whereas for a baseball, you can measure both the position and momentum very precisely. So this tells you that supposing you have a, uh, uh, a an electron and you say, well, I can measure the electron where it is to this speed, to this distance, then the speed can be measured only by up to this precision. But supposing I were to measure the particle to a sharper precision, position, then I don't know very much about how fast it's moving. So the more I know where the particle is, the less I know about how fast it's moving. And the more I know how fast it's moving, the less I know about where it is. So this is known as the uncertainty principle. And so the application of this is in optical microscopy. So in optical microscopy, you can take advantage of this by measuring the position of many particles of very small structures inside polyps, Spirogyra and Radiolarter in here. So you can see the distance here is just 50 micrometers. So you can see how powerful quantum science can be when you exploit it to make technologies. Now, let's me talk a little bit about um, uncertainty. What happens with electron interference when we take into account this idea of uncertainty? So when an electron passes through a very narrow slit like this, its momentum, we know precisely very well where this electron is going to pass through. So if we know very well where the electron is going to pass through, then we don't know its momentum or speed. So what happens is that on the other side of the slit, this electron becomes more wave-like, and so the momentum becomes uncertain. So this explains why you have electron interference, because once it passes through the slit, it becomes more like a wave, becomes more spread out. Now, what happens when we look at this wave fronts, electron waves, how do we imagine them? So we say, okay, an electron comes here, its wave is here like this, it proceeds, the wave expands, it hits these two slits, then you have smaller wavelets that come out, and these two wavelets will interfere, and that produces the interference pattern. Okay, we get that. But now, let me ask a question. Where is the electron? Okay, what do you think? Where is the electron? Well, I can't really tell you because it's just like a wave, right? So here the electron is, if when the wave's here, the electron is all here, is everywhere here. In this place, the electron is here and here. The electron is here. When it reaches a screen, it makes a certain dot. Okay, so until I make the measurement, I don't know where the electron is. It is in all these places at the same time. But what when I make the measurement? Where is the electron then? That leads us to this idea of measurement. So supposing I send in one electron, where is it going to hit the screen? I don't know. But what I can tell you is what is the probability. So if I have these electrons that are going through and they produce this interference pattern, the height of this probability wave tells me what is the likelihood of measuring this particle at this time. So this is the next idea in quantum mechanics. When you make a measurement, you don't know for sure what you're going to get, but you can know the probability of making that measurement. So that's called the probabilistic interpretation of quantum mechanics. So this is very unique because if I take a ball and I throw it, F equals ma tells me where it's going to go at a later time, right? If you have done some trajectory calculations or Newton's first law equations, you know how to do this. But I cannot tell you in quantum mechanics for a quantum particle, I cannot tell you where the particle will land, but I can give you its likelihood. I can give you the probability. So the idea behind this is that all electrons may be prepared identically, but they don't reach the same final place on the screen. So the same initial conditions do not give you the same final conditions. So it's like a wave on the sea. You may all start at the same place offshore, but it reaches different points on the shore. So this quantum behavior is indeterminate. Einstein did not like this idea. So he famously said, God does not play dice. Sorry, Einstein, you were wrong. It looks like quantum behavior is exactly indeterminate. This is how the quantum world behaves. But there is actually a more interesting idea. What if I could put a little measurement device or a demon or something here and say, I will know when the electron comes through the slit. Okay, so I just have an idea that I'm just going to keep track of when an electron comes to the slit. What happens then? Well, surprise, there is no interference pattern anymore. You only get it looks like a particle behavior. Well, let's say, okay, I'm going to look at electrons that come through this slit. Again, there's no wave behavior. I only see particle behavior. So the quantum measurement is a very interesting idea because what we're seeing is that matter exhibits both wave and particle natures, though not at the same time, and it depends on whether anybody's looking at it. So interference occurs when two paths are possible and there's no knowledge of which path the electron has taken. So this means fundamentally that the real world is essentially different when a detector is present and when a detector is not present. The detector does not have to be a human. It's just a possibility of detection that would change the behavior of the world. So this is a mind-blowing concept. And it leads to the most famous example of quantum mechanics, and that's quantum computing. You're going to learn about this quantum computing in the next few lectures, but it's set to revolutionize the way we do computing. And it's going to be able to let us solve problems that classical computers cannot do. And Canada is one of the leaders in the field of quantum computing. So, just to summarize what I told you, the features of quantum mechanics that we use are complementarity, which means that light and matter act both like a wave or and as a particle, but not at the same time. Uncertainty, that it's impossible to know exactly where a subatomic particle is and how fast it's moving. The more precisely you know one of them, the less precisely you know the other. And we can only know the probability of a particle being in a region of space at a particular time. So these are the features of quantum science that have revolutionized technology in the last century. So if you're watching this video online and you have questions, feel free to reach out to me by email. My email is rangan@uwindsor.ca, and I'll take questions in a minute. And I invite you also to the next lecture in the Quantum Science and Career series, which is going to be given by Dr. Svetlana Barkanova, and she's going to talk about quantum jobs of tomorrow, what you need to know today.